Let's just wait a couple of 1 minute. I think it just starts. It will take time. There'll be less of recording to watch for all those who are not attending. Right. It has started. Thank you. Okay. So out of this latent heat, can we find out how much percentage of this latent heat is going in water vapor and how much of this latent heat is going in the hot concentrated solution? 50% by weight NaCl solution, right? Whatever heat we are supplied is going in two places. One is it is going in vaporizing the water, and it is going in this heat, and the 50% by weight solution. So if you take reference condition for the salt solution, if you take the reference condition as 30 degrees centigrade, this will have zero enthalpy. Right? Then we can find out enthalpy of this water vapor at 117 degrees centigrade, assuming boiling point is 117 degrees centigrade, and enthalpy of this 50% by weight sodium chloride solution. Right? Can you tell me how much of it is going as a percentage if you want, or as a fraction, or just the values? How much of this latent heat is going in vaporizing the water, and therefore the water vapor will carry the enthalpy, and how much of it is going along with this hot solution? Can you tell me from your answers, from your calculations that you have done?
Sir, you mean the fraction, right?
Fraction, percentage, absolute values. Tell me anything that you like. Suppose I say latent heat is 100 joules. Out of the 100 joules of latent heat that I provide, how much of that is going in this? How much of that is going in this? Or if you want to tell me the actual value based on 112 kgs, you can tell me actual values in terms of kilojoules. Choice is yours. Percentage. Once you know the actual values, you can find out the percentages, right? Or fractions. What you answer is not important. The conclusion coming out of it is important.
Sir, it is 0.5% in the hot concentrated NaCl solution.
0.5% and 99.5%.
Yes, sir.
Okay. Let us just see if anybody else has got any other values.
So for the water vapor, it is coming as 85%.
Okay, 85%. And this is 15%. We have one answer 85, another answer 99.5 and 0.5. Any other answer? Praveen, just check your values.
Yes, sir.
So it is 0.5% and 99.5, sir.
Just check your values. Or maybe Who got 85? 85 and 15? You can also check your values.
So no, sir, my mistake. I was calculating just for the water. For the total solution, sir, it is 85%,
And 15%.
15%. Yes, sir.
So 15% in the hot solution and 85% in the water vapor, right?
Yes, about 14.5. But
That's okay. That's okay. 14.5, 15, they're fine. It's not the value that is we are looking at. Our next problem depends on this. This is going to be a source of our next problem. Any other answer? 85, 15, 99.5, 0.5? Any answer? What takes so long if you have solved the problem? That means many of you have not solved the problem.
Sir, we have solved the problem for wrong temperature 108 and
Arey, forget the
128.
temperature, re Baba. Forget the temperature. Even if you have solved it for wrong temperature, doesn't matter. This number will not change by much, even if you have solved for wrong temperature. You tell me whatever wrong temperature values you have, doesn't matter. If it is 108 degrees centigrade that you have taken, I don't know what is correct. Instead of 112, you might have got 105 or 107 or something like that. What did you get for the wrong temperature? I should not say wrong temperature, for a different temperature.
For
Sir,
Instead of 112, what did you get? Or you got 112 for the different temperature?
sir, actually for wrong temperature we get as the answer as 1 1, the triple one, and for the new temperature we get 112.
So instead
So
of
no much
112, it
difference.
is 111, right?
Yes, sir.
So
And
that
for
is
the new
even
answer
better.
it is
That is
112.
even better. 111 is exactly divisible by 3. So you get 37. Right? So whether it is right temperature, wrong temperature does not matter. All I want you to find out is out of this latent heat, how much of it is gone into water vapor and how much of it has gone in the hot saturated solution. That percentage will not change much. It will change only by maybe 1 or 2% or maybe even half a percent.
Sir, it's
Sir,
84-16.
84-16, right?
Yeah, yes, sir, same.
yes,
Right.
sir.
So
85-15.
sir,
right. So shall we say approximately 85 and approximately 15?
Yes, sir.
Yes,
Okay.
sir.
Do you all agree? Then we can go to the next problem.
sir, sir, I'm also getting 85 and 15, but when I don't consider the weight of the composition of the solution,
When you don't consider composition of the solution means,
when you don't consider that that the in the solution it has 50% of NaCl and 50% of water.
but okay, we can assume that the specific heat of salt solution is like that of water. So it doesn't matter. Composition doesn't matter. Is that okay then? Praveen, is that okay?
Sir, wait, I will rephrase my question. We
Okay.
can carry on.
No, no, no. You rephrase your question. Okay.
Sir, I meant
Okay, okay.
in
What did you mean?
stream 2, in
In,
stream 2,
uh,
the 99.5% of energy is going, and stream 3, 0.5% of energy is going.
which is your stream 1, which is your stream 2?
Stream 2 is the water vapor,
And stream 3 is salt
is
solution.
the salt solution.
So it is 99%, 99.5% and 0.5%.
Yes, sir. But when
But
you
you also
don't
told
consider
85
their
and
mass,
50. When you don't consider mass, how can you not consider their mass? Because their amounts are totally different, right?
then we get 85 and 15%.
You have to consider mass, no? Because the solution of 100 kgs, it is not that it is going as 50 kgs here, 50 kgs here, right? They are not equal amounts, right?
Okay, sir.
Do you agree, Praveen?
Okay, sir. I will.
No,
You
not
can
you
carry
will.
on.
No, not you will, Baba. This is an important doubt. This water vapor is 94 kgs and this solution is only 6 kg per hour. Isn't it?
Yes, sir.
So don't you think that we will have to consider their mass in terms of how much energy they are carrying?
Yes, sir. Then we getting 99.5% and 5%. If we don't consider them, then we are getting 85% and 15%.
Okay, so then everybody please check their values, whether it is 85, 15. I'm just going to put both values here. Maybe, or 99.5, maybe 0.5. Okay, I'm not sure. I don't know. I have not solved. Okay.
Sir, I also got 99.5.
Okay, fine. I mean, I have solved. I know the answer, but I'm not telling the answer. Whether it is 99.5 or whether it is 85, do you all agree that whatever latent heat we have supplied, majority of it is ending up in the water vapor? This is what is taking away, or this is what is taking up a lot of heat. Do you agree with that?
Yes, sir.
Yes, sir.
So if I have to reduce this 111, if I have to reduce this 111 to maybe something like 30 or 40, let's take the number that is divisible by 3. Suppose I reduce it to 30 kg per hour, then from 30 kg per hour, I will get 3 kgs of salt. So the cost of steam would just be 10 rupees per kg of salt. Do you agree with that?
Sir, can you repeat?
Okay, concentrate. Okay. Whatever latent heat we have supplied, more than 85% of it is going here and a small quantity is going here, whether it is 85-15 or 99.5 and 0.5. 99.5 is more than 85, right? So more than 85% is ending up in the water vapor and very little of it is ending up in the hot salt solution. Do you agree with that, Smith?
Yes, sir.
Now, because all the heat is going here, it has required 111 kg per hour of steam, which means 37 kgs of steam or 37 rupees per kg of salt produced. Do you agree with that?
Yes, sir.
Now, if I can reduce this 111 by some way, if I can reduce it to 30 kg per hour of steam, then I will require only 10 kgs of steam per kg of salt and cost would be just 10 rupees per kg of salt. Now, this is much more manageable. Do you agree with that?
Yes, sir.
So we have to think about how to reduce steam consumed. When I say steam consumed, which means we are talking about energy consumed. Steam is not consumed per se. We are getting water, which we can convert back into the steam. So how to reduce the steam consumed from 111 kg per hour to, let's say, to approximately 30 kg per hour? Is it not a good problem to solve?
Yes, sir.
Okay. Now, if I have to reduce this steam from 111 kg per hour to 30 kg per hour, don't you think I need to use this 85% of the heat and thereby reduce the amount of fresh steam required? Yes, no? Smith?
Yes, sir. Sir, we can use it in heating up the condensed water.
Right. So so that's our next problem. What are the different ways in which we can utilize the enthalpy or heat going out with 94 kg per hour of water vapor at 111 or whatever 108 degrees centigrade? Whether it is 108 or 107, 117, I don't care, right? Don't you think this is a good problem? Thereby we can solve
Yes, sir.
the cost of salt from 37 rupees to 10 rupees. Yes, no?
Yes, sir.
Now, Smith, can we go forward?
Yes, sir.
So one option Smith has already told. Smith, you only told, right?
Yes, sir.
One option Smith has already told to us that the salt solution this is one option that Smith has told, and we'll look at more options. Right. Option one Smith has told is to use this heat, take this condensed water, take this water vapor and give this heat to this condensed water in something called as heat exchanger. So what this heat exchanger would be like this. There will be a vessel in which there will be tubes. Something called as shell and tube exchanger. So this water vapor will be on outside of the tubes, and this condensed water can be going inside the tubes. So you have a hot fluid on the outside and you have a cold fluid which is going inside the tubes, and then heat gets transferred through the walls of the tubes. Can you visualize?
Yes, sir.
If you can't visualize, just do Google shell and tube heat exchanger. How does a shell and tube heat exchanger work? Okay. This is going to come anyway in semester 5 when you start looking at how heat is transferred and how do you calculate all these things. How do you find out the size required of shell and tube heat exchanger? Okay. But Smith, do you see a problem? What temperature this water vapor is coming out at?
117.
117 degrees centigrade. What temperature this condensed water is coming out at?
137.
137 degrees centigrade. So do you think something that is at 117 degrees centigrade can give heat to something that is at 137 degrees centigrade?
No, sir.
No. So
So we need to heat the water vapor above 137 degrees Celsius.
which means we will need to have some other source of heating, isn't it?
Yes, sir.
So you need to think more about this option. Rather than heating up this condensed water, can we not heat up this seawater? That seawater is fairly cold as compared to this water vapor. Don't you think we can use a heat exchanger in which we will take, let's say, seawater, put it through this shell and tube exchanger, right? It will go inside the tubes, get heated up, and take this water vapor and make it condense outside the tubes. Don't you think that is possible, Smith?
Yes, sir.
So this water vapor I will condense back into liquid water, and the hot salt solution, now seawater, will get heated from 30 degrees centigrade to maybe 80, 90, 100 degrees centigrade. And then now the amount of steam required can be less, because now it has, as far as this control volume is concerned, what it is seeing is, it is seeing seawater not at 30 degrees centigrade but at 100 degrees centigrade, and then only little amount of heat will have to be supplied to make it go into evaporating the water. Do you agree, do you agree, Smith?
Yes, sir.
So there is option 1. Anybody else can think of any other option?
Excuse me, sir.
Sir, we can
Yeah.
play with pressure.
Yeah, 1 second, Hardik, go ahead. 1 second, Praveen.
So please could you repeat the first process again?
Which process? First means
So
which
the
process?
seawater one, the seawater one.
Ye wala?
No,
This
sir.
one?
I'm asking about seawater at 90 degrees Celsius when we heat the seawater and it enters the uh, shell tube heat exchanger.
Right. What Smith was saying, is that you heat up this water. Smith, am I correct?
Yes, sir.
Smith was saying you heat up this water, 137 degrees centigrade water. Is that what you're asking, Hardik?
Yes, sir.
Now, what temperature this water vapor is coming out at?
117.
So can something that is at 117 degrees centigrade, can it give heat to water at 137 degrees centigrade?
No, sir.
No. Isn't it?
Yes,
So
sir.
I need to have a steam, I need to have a stream which is at a lower temperature than 117 to pick up the heat from this water vapor. Isn't it?
Yes, sir.
Now, do you see a stream which is at a temperature lower than 117?
Yes, sir. The seawater which was
seawater.
entering in the field.
Right? So instead of seawater entering at 30 degrees centigrade, I could use a shell and tube exchanger in which on the tube side, I will make the seawater go. It will get heated up from, let's say, 30 degrees centigrade to 100 degrees centigrade, or maybe 90 degrees centigrade, whatever you want. And this water vapor can be outside the tube. I will supply this water vapor at 117 degrees centigrade, and I will convert that into liquid water. It will give back the latent heat. Now, if you think about this yellow control volume, as far as the evaporator is concerned, it is not seeing seawater at 30 degrees centigrade. It is seeing seawater coming in at, let's say, 100 degrees centigrade. So to that extent, don't you think the amount of saturated steam that I'm going to require will reduce?
Yes, sir.
Right. Wasn't that our objective, to reduce it from 111 to 30?
Yes, sir.
Okay. So this becomes your homework problem. Can you find out the amount of steam required? And is it less than 111 or 100 and whatever that number was? Can it be reduced? To what extent it has been reduced? Can anybody think of any other option?
So reduce the pressure.
Where?
Sir, on the steam stream, sir.
Reduce the pressure here. Reduce the pressure of this steam
Yes, sir.
or this.
Water, sir. Sorry, water vapor at 117, sir.
So instead of operating this evaporator at a total pressure of 760 mmHg, we operate it at lower temperature and lower pressure. Is that what you're saying?
Yes, sir.
Why is that? Why do you want to say that? Why do you want to do that?
So 1 minute.
So we had said that total pressure was 760 mmHg, and therefore water boiling point is 100 degrees centigrade plus boiling point elevation made it 117 degrees centigrade. Hardik, instead of 760, you want to operate it at lower, let's say 500 or 400.
Sir, actually, I forgot what I was thinking about, sir.
Oh, okay. So think and tell me after 5 minutes.
Sir,
Anybody else can
sir,
think
if
of
we
any other
change
option?
the pressure of saturated stream, can the latent heat increase? Can it?
Okay, you want to change this temperature. So you want to keep this pressure at 760 mmHg, and you want to change this pressure.
So that the latent heat
Now
will
tell
be
me, what
increased.
pressure you want, higher or lower?
Sir, I had to think it first.
Huh?
Sir, not sure, but
Then first of all, 137 degrees centigrade, saturated steam. What is the pressure from steam tables? You have seen the video, or you have not seen the video of steam tables?
yes, sir, I've seen.
But you don't remember. So do you have steam tables with you?
Yes, sir.
So open your steam tables, and can you not tell me what is the saturation pressure corresponding to 137 degrees centigrade?
Sir, it's near 330 megapascal.
You are telling any random things that you like. Okay, are you able to see?
Sir, kilopascal, sorry. Kilopascal.
Are you able to see?
Yes, sir.
Yes. Yes or no? Say something, Re Baba. Are you
Yes,
people
sir.
able to see something, or you people
Yes,
are not
sir.
able to see anything?
Yes,
So
sir.
we can see.
Yes.
Yes, sir.
So then tell me no that you are able to see. Then only I can explain. No, this is not a normal class for this dumb idiot virus is created. All these nuisance that I have to talk in this bloody stupid idiot Google. This recording will not be shared. Well, okay, maybe I will edit and share. So if you see, look at this saturation temperature table, right? What is the temperature? 137 degrees centigrade. 137 is here. What is the pressure? 322 unit.
Sir, kilopascal.
Kilopascal, right? So 322 kilopascal means 3.2 atmospheres or 3.2 bar, if you like. Okay. Is that okay? Kilopascal and bar.
Yes, sir.
Okay. Okay. Fine. Fine. All right. Now let's go back to our problem. So this pressure is, let's say 3.3 bar absolute. 330 kPa, kilopascal, is same as 3.3 bar. Okay, now Praveen, tell me whether you want to increase this pressure or reduce this pressure. Praveen,
Sir, increase.
increase the pressure. Okay, so let's say we increase it to 5 bar, 10 bar. Say 10 bar, isn't it?
Yes, sir.
Okay, let's go back to steam table.
Sir, my main motive is to increase the latent heat
No,
only.
okay, na, okay, we will see what that happens. I can answer you in 3 seconds, but I don't want to answer you in 3 seconds. I want you to find out answer for yourself. So 10 bar. 10 bar means 1000 kilopascal. 1000 kilopascal is here. Do you see this?
Yes, sir.
So temperature would now be 180 degrees centigrade. Latent heat. This HFG is the latent heat. HF is the enthalpy of water. Are you able to see properly? HF is the enthalpy of saturated water. Hg is enthalpy of saturated steam. HFG is the latent heat. So if we look at 180 degrees centigrade, latent heat is 2013 kilojoules per kg. Do you agree with that?
Yes, sir.
Yes, sir.
2013. Just remember that number, 2013.
We have to
Whereas
decrease the pressure.
whereas at 136 or 137, 136, let's say, it was 2727. So 2700 versus 2013, which has higher latent heat.
Sir, the lower one, the 137.
137, isn't it? Sorry, I think it's not 2727. It is 136 was, I should look at the things properly. HFG was 2156. 2156 versus 2013. right? Is that okay?
Yes, sir.
So now tell me whether you want to increase pressure, whether you want to reduce pressure.
Sir, then reduce pressure.
But if I reduce pressure, what will happen to the temperature at which I am supplying steam?
So the temperature will decrease.
Temperature
Sir,
will
can't we
decrease.
keep it constant?
How can we? Steam table, Gibbs phase rule. Do you remember Gibbs phase rule?
Sir, not by the name, but I know the what happens.
If you look at this is where we started that steam table discussion. I have solid, I have liquid, and I have vapor. At 137 degrees centigrade, this is my saturated steam. All right. So Gibbs phase rule. Gibbs phase rule. Raveen, do you people remember? You people don't remember? ये सब किया है तुमने 11th standard में, मगअप किया है सब लोग ने. Nobody understands anything. Everybody has mugged up everything. Praveen,
Yes, sir.
C plus क्या? ये फेज रूल देखा है नहीं देखा है?
No, sir.
Sir, no, sir, not by the name. If you have read it.
ये कभी देखा नहीं है?
No,
F
sir.
plus phi, F plus P, और F is equal to, ये सब कभी देखा नहीं है?
No, sir.
No,
No,
नहीं,
sir.
No,
No,
sir.
sir.
Okay, ठीक है.
No, sir.
No, sir.
Okay, fine. I take back my words. This is known as Gibbs phase rule. So this is degrees of freedom. This is number of phases, number of components. This is just the 2 degrees of freedom that are there. Okay, we can derive this in thermo course. You will derive as well, but don't worry about it. So if I'm at this temperature, 137 degrees centigrade and 3.3 bar absolute pressure, how many phases are there? I have steam as well as I have condensed water, right? How many components are there? Only one, water. So what is the number of degrees of freedom? Just one. That means if I fix temperature, pressure will automatically be fixed. Or if I fix pressure at 10 bar, temperature will be automatically fixed 180 degrees centigrade. Because this relationship is given by Antoine equation, the temperature and pressure are related. Don't you agree?
yes, sir.
Yes, sir.
So if I change the pressure, temperature will automatically
Yes, sir.
change. If I want, I cannot change the pressure and keep temperature the same. Then if you want to keep it at 3.3 bar, or if you want to keep at 137 degrees centigrade and change the pressure, it will go here in a liquid state. Then that latent heat will not be available. If I keep it at 137 degrees centigrade and 10 bar absolute pressure, it will become liquid water. It will not be saturated steam. Do you agree, Praveen?
Yes, sir.
So temperature and pressure are interconnected because of this Gibbs phase rule. You can derive this. You will derive it in your thermo course. Okay. We will digress too much if we start deriving this now. Okay, now tell me, what do you want to do? Want to increase pressure? Want to reduce pressure? What do you want to do?
Sir, then there are problem in problem in both that direction then.
Correct. If I reduce it to 2 bar to increase the latent heat, this temperature will also fall. Then I will not get the 20 degree centigrade driving force that I wanted. In any case, I can't reduce it to too low a value, because then it will be less than this boiling point of water plus the boiling point elevation. So I can't do that. Just one hint. What is the pressure at which this water vapor is coming out? This water vapor is coming out from where?
Sir, atmospheric pressure.
So atmospheric.
Correct. It is coming from evaporator, right? Evaporator. What is the pressure of the evaporator?
760.
760. So this pressure, this also is 760 mmHg. That means this is 1 bar, 1 atmosphere absolute. One option, can we not compress this to 3.3 bar and then mix it with this? That way, the amount of fresh steam that I will require will be less, because anyway, this is 94 kg per hour, isn't it? And this I wanted was 111 kg per hour. So this we wanted as 111 kg per hour. So fresh steam would be required, would only be approximately 111 minus 94, maybe 17-18 kilograms. Do you agree with that? Yes or no?
Yes, sir, but we'll have to even heat this, right?
Yeah, so I will need to compress it to higher pressure. From 1 atmosphere absolute, I will compress to 3.3 bar. So I will require some electricity. Now the cost would be cost of this fresh steam plus cost of electricity. Isn't it? So if you just see, I require 111 kg per hour. I have got 94 kg from here, which I will compress to 3.3 bar. So this would be 94 kg per hour. So this would only be maybe 11 plus 6, 17 kg per hour. So the fresh steam that I require is only 17 kg per hour. But I require extra electricity. So the cost of that also I have to consider. Isn't it? Do you agree with that? Arya,
Yes,
is that
sir.
okay?
Yes, sir.
Okay. Anybody else? Everybody else? Okay? Not okay?
Okay, sir.
This is option.
Okay,
This is
sir.
option 2. This is option 2. Right. So in the problem sheets that I gave you, extra practice problems from the past papers, this option is also there. Okay. You can look at that. You can look at that. If anybody has seen that sheet. Anybody has seen that sheet?
Yes, sir.
Right. So this problem is there
Yes,
in that
sir.
sheet. Okay. Any other option? Anybody else can think of any other option? What are we doing? By doing this,
Sir?
by doing this, option 1, what Smith told, option 2, what Praveen was trying to do, are we not recycling our enthalpy? Are we not recycling our energy that was going out with this 117 degrees centigrade water vapor? Are we not trying to recycle that back by utilizing it to heat up the seawater? Are we not recycling that energy going out with hot water by compressing and putting it back into the process? Do you agree with that? It's a sort of a way of recycling our energy.
Yes, sir.
Yeah, somebody had some doubt. Somebody was going to ask something.
Yes, sir.
Yeah,
So
go ahead,
can't
Akshat.
we use a RO?
Yeah. I mean, using reverse osmosis is a different option only. But yes, you are right. You can use reverse osmosis, but reverse osmosis also will require some amount of energy. We will require pressure because seawater will have to be increased in pressure. So this is something that you will do in semester 3. No, not semester 3, semester 5, trying to look at membrane separation processes. Yes, reverse osmosis is an option, but right now we are not looking at that. We are looking at evaporation as one operation and trying to reduce the cost of evaporation. If we try to compare different processes, so membrane process can be one, or you may have any other process that separates salt and water. We are not trying to compare different processes, different operations per se, Rishabh. Is that okay?
Yes, sir.
But yes, as an engineer, you will have to compare different options, maybe evaporation, maybe membrane, maybe combination, maybe some other technique, and come out with a more economical process. But right now we are in first year only, so we will do only limited amount of we will only look at limited options just in the interest of time, because whole semester 5 is going to be there where you're going to look at membrane processes, because you need to understand something about membrane processes as well before you can start analyzing those. Rishabh, is that okay?
Yes, sir.
So, but good option. Keep your mind open that evaporation may not be the only process. I fully agree with you. Okay, anybody else can think of any other option? Any other option? Yeah.
So, like, why are we thinking that it would only take latent heat
Yeah, go ahead.
and not cool down further?
Go ahead, Arya.
We are assuming over here that the heat supplied is only in the form of latent heat. So, can we assume that even the temperature of water as liquid would drop in supplying heat?
Yes, but I told you, we wanted 20 degrees centigrade difference between this inside temperature and outside temperature. Boiling point was water boiling point plus boiling point elevation. If I allow this to come below 137, I mean, that's how we got this 137 degrees centigrade, right? We got this to be 137 degrees centigrade from there only, na? If I don't maintain the 20 degrees centigrade driving force, then I will require more of the evaporator. Then the cost of evaporation will increase. Cost of the evaporator will increase. But yes, you are right that we can subcool that water. I will tell you what you are probably thinking. You are probably thinking about that 15% that is going here, right? Can we think about this process that I have evaporator? This salt solution is coming here. This is going at 117 degrees centigrade. This is going at 117 degrees centigrade. This is steam at 137 degrees centigrade. This is water at 137 degrees centigrade. I have three hot sources. I have this hot source, I have this hot source, and I have this hot source. And I have seawater coming in at 30 degrees centigrade. Can I not use one more exchanger where that seawater will go inside the tubes? one more exchanger where seawater will go inside the tubes. Oops, sorry. This water vapor will be outside this exchanger. It will condense and give heat. Maybe then I will heat up the seawater to, let's say, 110 degrees centigrade. I will partly utilize this hot water as well. Not hot water, hot salt solution as well. Anyway, this hot concentrated salt solution, what do I need to do to get the salt out of it? Good morning. I have asked a question. This hot salt solution, what do I need to do to this hot salt
cool it.
solution to get the salt
Cool.
out of it as crystals?
Cool.
Right? Can I not cool it by heating this seawater?
Sir.
Sir, can we filter it?
And then solution, if you filter, do you remember this problem?
Yes, sir.
Did we filter the hot solution or did we cool so that the salt crystallizes out?
Yes, sir. Yes, sir.
Sir, we need to cool it.
Yeah. Solution means everything is inside the water phase. It is a homogeneous phase. If I filter that, nothing is going to happen. I'm going to get a filtered hot solution containing 30% or 50% salt. Praveen,
Yes, sir. I didn't check that.
only when I cool, it will precipitate or crystallize. Salt will crystallize because the solubility at lower temperature is less. Here, everything is soluble. That's why it is a solution. Here, the solubility is less. Therefore, it exists as crystals plus mother liquor, which is a solution. That solution contains 5-8%. Praveen, is that okay?
Yes, sir.
Can we go to energy balances?
Sure, sir.
Right. Now, look at all the possible hot sources that I have. I have one hot source, 117 degrees centigrade water vapor. I have another hot source, 117 degrees salt solution. I have another hot source, 137 degrees water. Can I not use all of this? One shell and tube heat exchanger, shell and tube heat exchanger 1, shell and tube heat exchanger 2. Can I not use that to heat up the seawater so that our control volume, this evaporator is concerned, the amount of steam required can be reduced? Do you agree or do you disagree?
Yes, sir.
Agreed, sir.
So now this is our option 3 possibly. What have I done? I have been able to reduce the steam consumption from 111 kg per hour to maybe, let's say, 30, 40 or 20 kg per hour. But I have used up additional equipment. What additional equipment I have used? I have used 2 shell and tube exchangers here. I have used compressor here. I have used one shell and tube heat exchanger here. Do you agree with that? To the
Yes, sir.
extent that we will use additional equipment, we can keep on reducing this steam consumption. So this additional expense, additional equipment is a one-time expenditure to buy and set up the plant. This is a one time. Once you buy it, install it, and set it up, then I don't have to buy again and again. Whereas the steam cost, it is incurred all the time that we are producing salt. If we are not producing salt, I will have no steam being used. But as long as I'm producing salt, I will have to buy steam. Do you agree with that?
Yes, sir.
This one-time expenditure to set up the plant is called as capital cost. This steam that is consumed all the time that we are producing is called as operating cost. It is incurred whenever I am operating the plant and making salt. Whereas this is only one time. Do you agree with that? These are just some two names. More about this capital cost, operating cost in semester 7. There is a subject called as chemical project economics. But I have been able to reduce the operating cost by increasing the capital cost, either for buying exchangers, compressor, plus this compressor also will be electricity cost. That is also an operating cost, because I will need to operate the compressor whenever I am producing the salt in this particular option. Do you agree with that?
Yes, sir.
Yes, sir.
So some kind of optimization is required, where this capital cost also, who's going to give me capital? I have to borrow from somebody, right? I can't borrow it from friend. I have to borrow from financial institutions, say banks, for example. This bank is not going to give me money for free, right?
Yes, sir.
What is bank going to charge?
Interest.
Interest, right? So interest I have to pay every year as long as I'm using this plant. So interest becomes an every year cost based on this capital. If I borrow 100 rupees from the bank, I will have to pay maybe 8 rupees of interest per year. If I increase expenditure by having more equipment, I will have to borrow maybe 200 rupees from the bank, and then I will have to pay 16 rupees of interest every year. But so the interest cost will go up as I use more and more equipment, but the operating cost of steam and electricity or whatever extra things are there, those will reduce. There is one more option. Let's look at that option as well. This was our option 3. option 4. Okay, let's look at one more option. This is my evaporator. Let me take you back. Let me take you back to some problem that we did earlier. Do you remember this problem?
Yes, sir.
Rather than doing evaporation in one evaporator, can we not do this evaporation in 3 evaporators? We will use more equipment.
Yes, sir.
Sure, we will use more equipment, but let's see if we can reduce the amount of steam consumed. So I will put that seawater here. This is our evaporator number 1. Seawater, this is at 3%. Maybe instead of what amount of water that we are evaporating, how much water we are evaporating? 94 kgs of water we are evaporating, right? So out of this 94 kgs, 1/3 we will evaporate here. 94 divided by 3. (94 divided by 3 is how much?
31.
31.
Thank you. We will evaporate 31.33 kg per hour here. This we will put it in second evaporator. We will again evaporate 31.33 kg here. This solution we will put to another evaporator. Here also we will evaporate 31.33 kg per hour. And then I will get 50% salt solution. Right? Do you agree with that? Now I will use steam here. I will get condensed water here. Now what would be the temperature inside the evaporator 1? What will be the salt concentration coming out of evaporator number 1? Hello, I'm asking a question. What will come out of evaporator 1? How many 3 kg per hour of salt will come plus water? How much water will come out of evaporator 1? 94 minus 31.33. Are you with me, or we are going too fast, or we are talking some Greek Latin?
So 97 minus.
So 60.
Yeah, sorry, 97 minus
8.67.
97 minus 31.33.
So 68.67 will come out of the.
What will be the salt concentration coming out of evaporator 1?
So it will be 3 kg.
Salt concentration. Concentration, Rishabh.
4%.
4 exact, Smith,
Yes,
or
sir,
some
4%.
4.3, sir.
4.3.
4.3 weight percent.
Yes, sir, 4.3.
4.37.
Yes, sir.
Okay. Second evaporator. It will have 3 kg salt. How much water it will have? 3 kg per hour of salt it will have, plus how much water it will have. And what would be the salt concentration?
So salt concentration would be 8%.
8%. And in the third one, it will get concentrated up to 50%. Do you agree with that?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So
Yes,
what is
sir.
going to be the boiling point of the solution in evaporator 1? Is it going to be 117?
No, sir, it will decrease.
It will decrease. Why? Because now the boiling point elevation is only going to correspond to 4.37 weight percent. Right? It will be less than 117. Maybe it is 103. I'm just saying some number. Don't take this number for granted. You calculate the boiling point elevation corresponding to 4.37 weight percent salt and boiling point elevation corresponding to 8 weight percent salt. Maybe this will be 109 degrees centigrade. And then this is 117 degrees centigrade. Now this steam, will it be at 137 degrees centigrade or something lower? I want to maintain a 20-degree difference. So if it is boiling at 103, the steam temperature should be
123.
123. Correspondingly, pressure will be lower. If you look at the steam table, I have the steam table open with me. So if we look at, let's say 123, steam pressure would just be, I'm looking at steam table, 2.1 bar. To that extent now, latent heat can be more. Praveen, you
Yes,
wanted to somehow increase the latent heat.
Yes, sir.
And now I don't have to evaporate all 94 kgs. I have to evaporate just 31 kgs, 31.33 kgs. So I will require much less amount of steam. Okay. This water is at, let's say 103 degrees centigrade, but a pressure of 760 mm Hg. Right? This is 760 mm Hg. Can I use it as a heating medium in the second evaporator? Is it not steam? Is it not superheated steam? So rather than calling it as water vapor, is it not superheated steam? Recall the video, what we mean by superheated, what we mean by saturated, what we mean by subcooled. At 760, it would have condensed at 100 degrees centigrade, but it is actually at 103 degrees centigrade. It has a 3 degree superheat. Okay. So this will condense at 100 degrees centigrade because the pressure is 760 mm Hg. But now if I want, so this will condense at 100 degrees centigrade. So if I want 20 degree difference, this evaporator has to be boiling at 80 degrees centigrade. Then only I can maintain a 20 degree driving force. Otherwise, if I maintain this at 1 atmosphere, suppose it was at 1 atmosphere, then this would have been maybe at 109 degrees centigrade. There is no way that I could have used this water vapor, which is at 103 degrees centigrade, to give heat to something that is at 109 degrees centigrade. So I need to reduce the pressure so that this water plus the 8% salt, according to boiling point elevation, boils at 80 degrees centigrade, so that I can maintain a 20 degree difference between the water that is at 103 condensing at 100 degrees centigrade and the boiling temperature. So this water vapor coming out of the second evaporator now will be at 80 degrees centigrade. isn't it? Can I not use it in the third evaporator, jacket of the third evaporator, and condense it? Now this is at a pressure less than 760 mm Hg. So this boiling point, condensed water coming out of the jacket of third evaporator will also be less than 80 degrees centigrade. So that means I have to operate this third evaporator at even more reduced pressure, even less or lesser absolute pressure. So that this will have a boiling point, considering the boiling point elevation to be maybe 16 degrees centigrade or 20 degrees centigrade, less than 80 degrees centigrade, isn't it? So this will be at even lower pressure. But then I have utilized this heat. I have utilized heat from here, and I'm sending this to atmosphere. So I may waste that heat because it's already at a low temperature, 60 degrees centigrade, right? Thereby, the amount of steam consumed will be even lesser. So this is called as a multiple effect evaporator. Okay. There is a video of this problem and a video of the solution. Okay. But don't look at the solution video, or maybe solution video I will post after 1 week or so. This video problem, you can see, I will post that immediately after the lecture, and you can solve that problem. Solution I will post next week.
Oh, so
Yeah.
so
Yeah,
instead of that, instead of directly introducing the water vapor to the jacket, can we first compress it rather than reducing the pressure of the evaporator?
Yeah, absolutely. So either you reduce the pressure of the evaporator, or you operate the evaporator at 1 atmosphere only and use a compressor here. That becomes option number 5. Good idea, Sarthak.
Thank you, sir.
Right, but the problem that we'll do is without the compressor. Compressors are always troublesome equipment, whereas reducing the pressure is an easier option. Don't worry about that, why it is so. Let us not get into that just now, because that will come in next semester anyway. Okay, so this is your homework. So how many homeworks do you have? Bapre. Every option there is a homework. Right? So at least 3 or 4 homework problem. So first homework is to calculate the boiling point elevation properly. Second option is to, second homework is option 1, use 1 shell and tube exchanger. Homework 3, option number 2, use compressor. Option 3, use 2 heat exchangers. That is homework 4. Homework 5, option 4, multiple effect evaporator. So you have 5 homework problems. Okay. What we have seen today, concepts. Is to think about where energy is going and how to reuse energy going out. That is a concept. Either we use the energy going out by option number 1, by using it to preheat the seawater, or option number 2, reuse the heat by compressing it to a higher pressure. Sure, we will use slightly more energy, we will use the electricity as well, but we are reusing the heat. Option 3, we are reusing the heat going out with water vapor. We are reusing the heat going out with salt solution, hot salt solution, because anyway that hot salt solution we have to cool to crystallize out. So it's a win-win situation. I need to heat the seawater and I need to cool the hot salt solution. So I'm doing both the things in one exchanger, one heat exchanger, by exchanging heat. It's a win-win situation. I have cooled the hot solution to crystallize, and I have heated up the salt water to seawater to reduce the amount of steam required. Fourth option is to use multiple effect evaporator. Right? So that's the concept that we have learned. How do I quantify where the energy is going? And how to reuse that energy by using extra equipment to preheat something, to heat up something, to exchange heat using heat exchangers. Okay. It was quite a heavy discussion for 1.5 hours. So if you want a break of 5 minutes, we can have a break of 5 minutes. Else we will continue. These are important concepts that we are looking at. Do you want a break of 5 minutes?
Yes, sir.
Right. So it is 10 o'clock. Maybe take 10 minutes. 10 minutes break. So we break up to 10 minutes past 10, another 10 minutes or 9 minutes. Okay.
Okay, sir.
But just think about, don't lose the focus. Don't use these 10 minutes or 9 minutes to play some video games or computer games. Don't play PUBG in these 9 minutes. Rather, you can have a glass of water, but think about what all things that we have said. Okay. Don't lose the concentration. Don't lose the effect of the classroom. Right. So now we will start looking at energy balances with reactions. Okay. We meet after 8 minutes. Anybody has quick doubts, quick questions? Quick doubts, some quick questions. Nobody has any doubts, which means everybody has understood everything. Or okay, shall we start?
Yes, sir.
Okay, any quick doubts up to so far? Any quick doubts with all these things so far? The doubt has come in the 8 minutes that you reflected upon. This is something that we don't do. We don't reflect. We don't think about what we are being doing. We mechanically do. We think that there are some problems to be solved, some formula to be applied to get some goal, to get some marks, right? That's not what we want to do. We want to reflect so that you can think, learn concepts, so that you can innovate and do something new. Think about a new way of doing things. Like who was saying? I think Rishabh was saying, right, that we don't evaporate water, we use membrane. Rishabh, is that what you were the one saying? I don't remember now who was saying. It would have been so much easier in class. Rishabh, were you saying, who was saying use membrane? Right. So
Sir, it was him only.
yeah, Rishabh only. So that's the objective of education, that we do something new, isn't it? Solve a problem that we have not solved, not get marks in an exam. To do that, we need to reflect on what concepts we are learning. Okay, let's go to the next part of the course and last part, or maybe second last part of the course. Our course is nearing completion. Okay, but our course will never be complete because the concepts can be discussed, but you need to apply and you need to practice and you need to solve problems. That will happen lifelong, not just with the end of the semester. It will happen, continue in next semester and next semester and next semester and next semester. And throughout your life, whenever you are solving problems, you will need to use material balance, you will need to use energy balance. So you are learning the course not in a matter of 60 hours. In a matter of 60 hours, you are just going to see the surface of the course. As you go along, you will keep on doing material balance, energy balance, and you will keep on learning from this course or learning this course. So the course will be completed maybe after 10 years of you graduating, when you have been able to successfully apply it to many situations. Okay, shall we look at energy balance with reactions now? So think about some reaction, right? Maybe I will say the reaction is SO2 plus half oxygen giving me SO3, right? Couple of things uh, that are here, or let me take one more example. Okay, let's talk about this, then we will take one more example. So if you think about, this is your reaction, right? SO2 in the gas phase reacting with oxygen in the gas phase, and we are getting SO3 in the gas phase. So what is important is the state in which we are writing the components and the reactants and the products. Of course, the stoichiometry for material balance, right? Third important concept is what are the heat effects associated with the reaction. Okay, what I mean by heat effects is, we have seen this reaction. Do you think this reaction is exothermic or endothermic? Do you think this reaction is exothermic or endothermic?
Exothermic.
Exothermic.
You don't sound very confident. Maybe you are asking a hesitant question. Maybe is it exothermic?
So I have
kind
many
of
factors in
hesitation.
mind, but I'm not sure. That's why.
There
Sir,
was a kind
exothermic, sir.
there was a kind of hesitation in your voice. Okay, Hardik, you are saying exothermic?
Yes, sir.
Okay. Anybody else?
Combustion reaction, so exothermic, sir.
Combustion reaction.
So bond formation, sir. That's all.
Well, we are seeing so many big statements. Rishikesh has said that it is combustion reaction, so it must be exothermic. Am I right? That's what Rishikesh you wanted to say, or who was saying?
Yes, sir, I was.
You were only saying. Hardik, you were saying bond formation. Who was?
Yes, sir.
No,
So I, sir.
What bond formation?
So between SO2 and oxygen forming SO3.
Okay, so extra bond is formed. So
sir, energy is liberated.
Why should that be? Extra bond is formed, so why should energy be liberated? Yeah, I mean, you are right, more or less. That gets into a more of thermodynamics, but you are qualitatively, yes, you are right. It is an oxidation kind of reaction. Usually the oxidations are exothermic, and hydrogenations are highly exothermic. So we quantify this reaction, whether it is exothermic or whether it is endothermic, by a term called as delta H of reaction. Are you aware of this? You must have used this in your 11th standard and 12th standard.
Yes, sir.
Yes, sir.
Yes, sir.
So if it is exothermic, what do we say about delta H, heat of reaction?
It would be negative.
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 Right? So that means it is negative. If it is endothermic, that means delta H for the reaction is greater than 0 or positive. Okay. Exothermic, what does that mean? Exothermic means heat is generated when products are formed. Hardik, is that what you wanted to say? Hardik or Rishikesh, is that what you wanted to say? When it is when it is endothermic, we need to supply heat, and if you don't supply, it will cool down. Products will be at a lower temperature. So if it is exothermic reaction, I need to, heat is generated. That means to maintain isothermal conditions, I need to take away heat. And if I don't take away heat, the products will be at a higher temperature. And do you agree with that?
Yes, sir.
Yes. No. I need to, if it is exothermic, I need to take away heat to maintain isothermal. And if I don't take away the heat, products will be at a higher temperature. Isn't it? If it is endothermic, I need to supply heat to maintain isothermal. And if I don't supply heat, the products will cool down. Right? Do you agree? Only 3-4 people are, I think, listening to the lecture and awake.
Sir,
Only
it may
3-4
also
people
change
are
the
answering. Yeah.
Sir, it may also change the reaction also, like the temperature change.
Yeah, if the temperature changes, yes, some other reaction may happen. In this particular case, no other temperature is happening, no other reaction is happening. But yeah, I mean, some cases your products may go further, get oxidized, or your reactants may undergo some side reaction. But right now, we are not worried about that. We are only talking about one reaction, one particular reaction. Right? Is that okay, Arya?
Okay. Yeah. Understood, sir.
Yeah. Only 3-4 people are listening. Arya is listening, Rishikesh is listening, Hardik is listening, Praveen is listening, Mayur is listening partly. Nobody else is listening. Can I safely make this statement?
No, sir.
No.
Yes,
No, sir.
Oh, good. Nishant is also listening. Yeah. In between, Ria was also listening. She also answered something in the middle. Oh, great. Thank you, Ria. Yeah, I'm just wanted to make sure that everybody is awake and listening. All right. So how do you find this heat of reaction? Don't you think it is important to know this heat of reaction, whether it is endothermic, whether it is exothermic, how much is the value? Depending on that, we need to decide how much heat I need to remove, or depending on that, how much I need to supply. Right? Suppose heat of reaction is minus 100 kilocalories per gram mole of SO2. That means every 1 gram mole of SO2 reacts. Suppose this is not actual value. Suppose I will tell you the actual value. Suppose it is minus 100 kilocalories per gram mole of SO2. That means when 1 gram mole of SO2 reacts, 100 kilocalories of heat is liberated, heat is generated, and I will need to take away 100 kilocalories of heat to maintain constant temperature. If I take out 90 kilocalories only, then temperature will rise. If I take out 110 kilocalories, temperature will fall. Okay. Anyway, we will do all these calculations, so don't worry about it. Or if the heat of reaction is, let's say, 45 kilocalories per gram mole of oxygen, that means when 1 gram mole of oxygen reacts, 45 kilocalories of heat will have to be supplied to maintain isothermal conditions. And if I don't supply 45 kilocalories of heat, if I supply only 40 kilocalories of heat, the products will cool down. Okay. So two things are important. One thing that is important is the sign, whether it is negative or whether it is positive. And we don't write that positive sign. If we don't write a sign, it is understood that it is positive. If it is negative, we have to write. So negative means exothermic, positive means endothermic. Right? Next thing that is important is the value. How much is removed? 100 kilocalories is removed. Per what? Per gram mole of SO2, per gram mole of something, or per gram mole of oxygen. Obviously, these two cannot be the same. Obviously not for this reaction, but in general, I'm telling you, there are three things that we need to look at. The value of delta H, whether it is negative or whether it is positive, the value in terms of kilocalories, and per watt, per gram mole of what. It could be defined on the basis of per gram mole of SO2, or it could be defined on the basis of per gram mole of oxygen, or per gram mole of SO3. I can define it in any way that I want. Okay, we will come to this as well as we go along. Can we go forward?
Yes, sir.
Yes, sir.
Okay. So the next question is, how do you find this heat of reaction? There are something called as standard heats of formation. And there are some things called as standard heats of combustion. Okay, the word standard, unfortunately the word standard has no standard, because everybody defines standard, or every subject defines standard in different way. In context of this heat of reaction, this standard is defined as 25 degrees centigrade and 1 atmosphere absolute pressure. That is the meaning of the word standard in context of heats of reaction. The word standard in terms of temperature and pressure is 0 degrees centigrade, 1 atmosphere absolute when we are talking about gas laws. Okay, so the word standard can be misleading, can be confusing, because it is taken in a context of what we are talking about. So at the standard conditions, which means 25 degrees centigrade, 1 atmosphere absolute pressure, we are going to say that substances, elements in their natural gas, in their natural states, natural state means at these standard conditions have zero enthalpy, isn't it? Is that this you have seen in your 12th standard, 11th standard?
Yes, sir.
Right, so that's one. So heats of formation, so if I say heat of formation, standard heat of formation of SO2 gas, if I tell you this value, standard heat of formation of SO2 gas is minus 296.90 kilojoules per gram mole of SO2, or and if I say standard heat of formation of SO3 gas is minus
Just because its name has a nut, it is not.
395. Arya, you can mute yourself. Arya, you can mute. Yeah. Minus 395.18 kilojoules per gram mole of SO3. Okay. Now, when I say standard heat of formation of SO2, what I mean is, if I write this reaction, sulfur in the solid form plus oxygen in the gas form, giving me SO2 gas, heat of this reaction is the heat of formation of SO2 from the elements in their standard state. This is minus 296.90 kilojoules per gram mole. And if I say standard heat of formation of SO3, what I mean is sulfur in the solid state plus 3/2 oxygen in the gas state is giving me SO3 gas. This reaction has a heat of reaction of minus 395.18 kilojoules per gram mole of SO3. Right? That's what we mean by standard heats of formation. Formation from what? Formation from elements in their standard state, because this has zero enthalpy. This has zero enthalpy. Our definition. Right? So how do you find heat of this reaction? So now heat of reaction of SO2 gas plus half oxygen gas giving you SO3 gas. How do you find heat of this reaction? This reaction I can write in terms of two reactions. So reaction 1 and reaction 2. If I write reaction 2 minus reaction 1, I will get this reaction. So heat of reaction for this particular reaction is nothing but delta H for reaction 2 minus delta H for reaction 1. And delta H for reaction 2 is nothing but delta H for reaction 2 is nothing but heat of formation in the standard state of SO3 gas minus delta H in the standard state formation of SO2 gas. So this is nothing but minus 395.18 minus 296.90. All right, do you agree with that? You can actually find the value. Don't worry about what the value is. So this is how we would use the standard heats of formation. So heat of reaction would be heats of formation of products minus heats of formation of reactants, and all reactants put together and all products put together. This you have seen in your 11 standard and 12 standard. Yes or no?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes,
Yes,
sir.
sir.
Excellent. Or heats of combustion, if I write. Heat of reaction, I can write in terms of heats of combustion is standard heats of combustion for all the reactants minus the standard heats of combustion for all the products. Do you agree with this? We had also seen this in your 11 standard and 12 standard. Yes, no?
Yes, sir.
Yes, sir.
Yes, sir.
Okay,
Yes,
so
sir.
we will stop here for the day. Revise another homework. Revise basics of thermochemistry from your 11 standard and 12 standard. Okay. Shall we stop for the day?